Hi everyone, welcome back for today's class. Last class, we were discussing about equipotential surfaces. So, I'm giving a flashback about the last class. Equipotential surfaces. What are equipotential surfaces? EQ equal, potential, same potential. So, equipotential surfaces are surfaces of constant potential. On such a surface, there is no potential difference. Okay, and we learned properties of equipotential surfaces. Two equipotential surfaces never intersect. Why they never intersect? If they intersect, at the point of intersection, there will be two directions for electric field, which is not possible. At one point, there can be only one direction for the electric field. What was the second property? The work done to move any amount of charge on an equipotential surface is zero, because no potential difference between any 2 points on an equipotential surface. Work done is Q into potential difference. Since potential difference is zero, work done is zero. And we have drawn the shape of the equipotential surface due to different charge configurations. What is the shape for equipotential surface for a point charge? For a point charge, equipotential surfaces are spherical surfaces. This is the equipotential surface for a point charge, spherical surface. And we have drawn the equipotential surface for a uniform electric field. For a uniform electric field, equipotential surfaces are plane surfaces, parallel planes. So these planes are the equipotential surfaces for a uniform electric field. And equipotential surface for a due to a dipole. Dipole equipotential surface is like this. Now for equipotential surface for a system of two charges, positive charges. Okay. So once again, I'm listing the properties of equipotential surface. Number one, the amount of work done to move any amount of charge on an equipotential surface is zero. Second property, no equipotential surfaces intersect. No two equipotential surfaces intersect. Why they are not intersecting? If they intersect at one point, there will be two directions for electric field at that point, which is not possible. Then, third property, electric field is always perpendicular to equipotential surface. Why it is so? Suppose this is an equipotential surface. This is a conductor, equipotential surface. surface of a charged conductor is an equipotential surface. So electric field has to be perpendicular like this. If it is not perpendicular, what would happen? See, suppose electric field were in this direction, making an angle theta with the surface. Then this electric field you can resolve into two components. E cos theta along y-axis and E sin theta along x-axis. This component E cos theta will make the charges move along the surface. But it is not possible because on the surface of an equipotential surface, potential difference is 0. So charges cannot move. Okay, that is why equipotential surfaces are always perpendicular to the electric field. So these were the properties of equipotential surfaces. This is only a recap of the last class. So we have learned this in the previous lesson. Today, we will discuss potential energy of a charge. Potential energy of a charge. Today's topic, potential energy of a charge. Potential energy of a charge. See, when you consider a charge Q, and you all know surrounding the charge there is electric field. Okay? What is the meaning of that electric field? If we move any other charge towards it, that charge will experience a force. So to move a charge in the field, to move another charge in the field of this charge, we need to do some work. Okay? If we move a positive charge in the field of this charge, we need to do work against the repulsive force, right? This work done is stored in that charge as its potential energy. So this is a charge Q. I call it a source charge. I am moving another charge, say Q0. Okay, to move Q0 towards this charge Q, I need to do work against this repulsive force. That work done is stored in this charge as its potential energy. Okay, so what is the definition for potential energy? It is the amount of work done to move a charge from infinity to the particular point. We have learned what is potential. You learned what is potential. It is the amount of work done to move unit to positive charge from infinity to that point. So potential energy is defined as the amount of work done. Potential energy of a charge is defined as the amount of work done to move the charge from infinity to the particular point. So that is a definition for potential energy of a charge. So I will write the definition here. Potential energy. Potential energy of a charge. Potential energy of a charge is defined as the amount of work done to move the charge, from infinity to the particular point without acceleration. And we learned the equation for potential. What was the equation for potential? V is equal to W by Q0. Q0 is the test charge. So what this work done, W equals V into Q0. This is the potential energy. Okay. So this is the potential energy of the charge. W equals VQ0. This work done is stored in the charge as its potential energy. So what is the equation for potential energy of the charge? W equals V into Q0. Okay. Now we are going to find out the potential energy of a system of 2-point charges. Potential energy of a system of 2-point charges. See, it is the amount of work done to assemble the charge, the two charges, from infinite separation to the present separation. So what is the potential energy of a system of two charges? It is the amount of work done to bring the charges from infinite separation to the present separation. So how will you find out? So next heading I am writing potential energy of a system of 2-point charges. So what is the potential energy? We have to calculate the work done to bring the two charges from infinite separation to the present separation. That work done is the potential energy of the system of two charges. So first I am bringing a charge Q1 from infinity to this point A. What is the amount of work needed? We assume that there are no other charges. Okay. We move Q1 from infinity to the point A. Since there is no other charges, there is no other field. We can say there is no other field or no other charges. So work done is 0. So work done to bring charge Q1 from infinity to the point A is 0. Now I am moving a charge Q2 from infinity to this point B. Now you have to do work against the force of the charge Q1. Suppose the distance between these two charges is R, say I am taking R12, distance between 1 and 2, R12. So to move a charge Q2 from infinity to the point, we need to do a work against the force of Q1. Okay. So what will be the equation for that work? You can apply the previous equation. W is VQ0. V into Q2. V into Q2. V1 is the potential at the point B due to the charge Q1. So we can use this equation. Okay. So work done to bring Q1 from infinity to the point A is 0. Why it is 0? Initially, there were no charges. So 0 work must be done to bring Q1 from infinity to A. Now we are bringing Q2. Work done to bring Q2 from infinity to the point B. For that, we had to use the above formula. What is that work done? I'm writing W12. It is potential due to first one, V1 into Q2. And you know the equation for potential, 1 by 4 pi epsilon 0 Q1 by R12 into Q2. So this work done is stored as the potential energy of the system. This work done is stored as the potential energy of the system. I think now the concept is clear. So what is the equation for potential energy of a system of two charges? 1 by 4 pi epsilon 0 Q1 Q2 by R12. Potential energy we did usually denote by the letter U. So potential energy we can write 1 by 4 pi epsilon 0 Q1 Q2 by R12. So this is the equation for the potential energy of a system of 2-point charges. Now we will find the potential energy of a system of 3-point charges. So potential energy of a system of charges. What is the definition for that? It is the amount of work done to assemble the charges from infinite separation to the present configuration. Okay, that is equal to the potential energy of a system of charges. Now I am going to find the potential energy of a system of 3-point charges. So next heading we can write as potential energy. System of 3-point charges. So here there are 3 charges. We are bringing these 3 charges from infinity to the present configuration. Okay, and we are going to calculate the work done. First, you bring the charge Q1 from infinity to the point to a point A. So this point A, I am bringing charge Q1 from infinity to this point A. Now there are no other charges, so no need to do any work. So work done to bring charge Q1 from infinity to the point A is 0. Okay. Now I am bringing the charge Q2 from infinity to this point B. Now you have to do a work because there is a force due to Q1. You have to do work against that force. That work done, you know the equation V1 into, suppose this charge is Q2, V1 into Q2. Okay. Now I am bringing a third charge from infinity to the point C, charge 3. Here, to bring the charge from infinity to charge Q3 from infinity to the point C, you need to do work against the force of Q1 and work against the force of Q2. Now we add all these work. Then we get the total potential energy of the system. And I am joining the distance between them. Say this distance is R12. This distance is R23. And this distance is R13. Now I am calculating the potential energy. First, work done to bring the charge Q1 from infinity to the point A is 0, because initially there were no other charges. Now you are bringing work done to bring the charge Q2 from infinity to the point B. Here you have to do work against the force of Q1. So we can use the equation for work done as, suppose first work done is W1, this work done is W12. It is, what will be the equation? V1 into Q2. That is 1 by 4 pi epsilon 0 Q1 by R1 into Q2. Now we have to bring the third charge Q3 from infinity to the point C. Here we need to do work against two charges. We have to do work against the force of charge Q1 and the work against the force of charge Q2. So we can write work done to bring the charge Q3 from infinity to the point C. So that work I am writing as W13. Here I need to do work against Q1, against the force of Q1. That work is V1 into Q1 plus V1 into Q3. That is V1 into Q3. We are moving Q3. Similarly, we have to do work against the force of Q2. So we can write that as V2 into Q3. Okay. So we can write this as 1 by 4 pi epsilon 0 Q1 Q3 by R13 plus 1 by 4 pi epsilon 0 Q2 Q3 by R23. Now potential energy of the system is the sum of all these works. Okay. So the potential energy of the system is U. Add all this work, W1 plus W12 plus W13. Okay. When you are adding, you can take the term 1 by 4 pi epsilon 0 common. So what will be the answer? So you add all this. Okay. W1 was 0 plus 1 by 4 pi epsilon 0 Q1 Q2 by R12 plus 1 by 4 pi epsilon 0 Q1 Q2 divided by R12 Q1 Q3. Sorry, Q1 Q3 by R13 plus 1 by 4 pi epsilon 0 Q2 Q3 by R23. U is equal to 1 by 4 pi epsilon 0. Common you can take Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. This is the equation for potential energy of a system of 3-point charges. Okay. So how will you find out the potential energy of a system of n charges? You have to find out the work done to bring all these charges from infinity to the present configuration. That will be the potential energy of that system. Okay, children. I think this is clear to you. This is very important. And I will do a numerical from textbook. A textbook example we will do. This is an important question. Okay. Example 2.4. Four charges are arranged at the four corners of a square of side A, B, C, D as shown in the figure. Find the work required to put together this arrangement. Second part of the question, a charge Q0 is brought to the center of the square. Four charges being fixed at its corners. How much extra work is needed to do this? Okay. So the diagram also will be given. So this is a diagram. Okay, we have to find out the work done to arrange this system. So here first you have to bring the charge plus Q from infinity to A. That work done is 0. So that I am writing as WA 0. Now we have to bring charge B. So when initially there were no charge. Okay, I brought A charge plus Q to the point A. Work done is 0. Now I am bringing the charge B from infinity to the point B. So you need to do work. That work I am writing WB. You have to do work against the force of charge A only. Equation you know, 1 by 4 pi epsilon 0 Q1. Q1 is Q. Q2 is minus Q by distance between them is side of the square given D. Okay. Now I'm bringing the charge C from infinity to the point C. Now we have to do work against force of A and force of B. So what will be WC? First work done against the force of B. What will be that? 1 by 4 pi epsilon 0 plus q into minus q by d, plus you have to do work against the force of A. What will be that? 1 by 4 pi epsilon 0. Q1 is Q plus Q divided by the diagonal. Distance between A and B, the diagonal only. That diagonal, you know, d root 2. Diagonal of a square, d root 2. Okay. Now, I am bringing the charge d from infinity to the point minus q. We are bringing the charge minus q from infinity to the point d. You have to do work against the fields of three charges: charge at A, charge at B, and charge at C. So I am writing that as WD. Okay. First work done against the force of A. What is the equation? 1 by 4 pi epsilon 0 Q minus Q. Charge between A and D. The distance between A and D is D. Okay. Then you have to do work against the force of C. What will be that? 1 by 4 pi epsilon 0. Charge is minus Q plus Q divided by D. Then you have to do work against the force of charge at B. 1 by 4 pi epsilon 0 minus Q by diagonal is root 2D. Plus you have to do work against so we are done work against A, work against B, then one more term is there. Okay. So now total potential energy, how will you do? We have to add all these terms. Total how many terms will come? 1, 2, 3, 4, 5, 6 terms will come. Okay. So we have considered all charges now. So what is the total potential energy? Add all this work. Potential energy. Okay. When you are adding, see, first term is what? 1 by 4 pi epsilon 0 minus q square by d. Then again, there is one more term, this one, 1 by 4 pi epsilon 0 minus q square by d. See, these four like terms I am adding first. So what will be the potential energy of the system? U is equal to, you know, when you add all the works, that four like terms I am adding. 4 into 1 by 4 pi epsilon 0 q into q, that is minus q square divided by d, plus now what are the remaining two terms? These are remaining two terms, this one and this one. So we can write 2 into q square 1 by 4 pi epsilon 0 q square by root 2d. Okay. So this is the total potential energy of the system. From this, we can take 1 by 4 pi epsilon 0 d common. What is the remaining? Q square also take out. what will be remaining? You are getting 2 by root 2 minus 4. Okay, so 1 by 4 pi epsilon 0 q square into 2 by root 2 is root 2 minus 4. So this is the potential energy of the system of charges. Okay. Now, so this is how you find out the potential energy. Now there is one more question. What was the second question? You have to find out how much a charge is. See the second question, B part. A charge Q0 brought to the center E of the square. 4 charges held at its corners. How much extra work is needed to do this? Now you are bringing a charge Q0 to the center. And you know the equation for work done. For this, the equation is V into Q. What is that V? Total potential at the center due to all the 4 charges. Okay. So how will you find out the extra work done? You need to find out the total potential at the point E due to all the charges into the charge Q0. So we can write part B, extra work done. What is the equation? V into VE, potential at the point V into Q0. See, you have to calculate the total potential. You know, there will be potential due to the 4 charges at the center of the square E. You can see the distance from one corner to the center is R. Okay. All this distance R only. Same distance. So potential due to all the charges will add up at the point E. So what is V? 1 by 4 pi epsilon 0 Q for the charge A, potential due to the charge A is Q by R. Potential at the center E due to the charge B is 1 by 4 pi epsilon 0 Q by R, plus potential at the point E due to the charge C is 1 by 4 pi epsilon 0 Q by R, plus potential at the point E due to the charge minus Q at the D, 1 by 4 pi epsilon 0 Q by minus Q, that is minus Q by R. You can see that all these terms cancel out. This cancel out. This into Q0. So what is the extra work done? 0. Okay. Because potential at the center E of the square will be the sum of potential due to all charges at the corners. So total work done is 0. Okay. This question is an important. So dear students, thank you for watching. Today I am stopping. Goodbye. We will meet again.